We'll be talking on the third part of the course, which is atmospheric thermodynamics. Relax your mind, because when students see thermodynamics, what will come to your mind is mathematics again. But as much as possible, since you are in environmental sciences, we'll make sure that the mathematics will be so friendly, not too tough, difficult for you to understand. So I deliberately skip details of calculus and all sorts of things that will cause headache for anyone that is not in good, not so good in mathematics. So before we proceed, these are the topics we are going to cover under the atmospheric thermodynamics for section 3. So the first one is the why we need to study atmospheric dynamics, and then what is ideal gas. The question of state hydrostatic balance, then heat and temperature, conduction, convection, radiation, and when we talk of heat, so we have to mention conduction, that is conduction of heat, convection, and then radiation. Water vapor in air, then latent heat, adiabatic process, and the last one will be Laplace rate and stability. That is the entire topics we are going to cover under this subject. But before that, as environmental scientists, why do I need to study atmospheric thermodynamics? And what do you mean by atmospheric thermodynamics? Does anybody have an idea of what atmospheric thermodynamics is before this class? Any idea? You've never heard the word thermodynamics before? Have you heard the word thermodynamics? Yes. You have no experience. Thermodynamics? Idea? Nobody. Huh? You've not heard thermodynamics before. Have you heard of it? In any way, you have never come across the word thermodynamics. There are just two words. Thermo means what? Heat. And then when you say dynamics, what is the meaning of dynamics? Something that is not static. Something that is not stagnant. Just like our clock. Your motion as you move every day. You didn't stay in one place, you move from one point to the other, one place to the other. The clock keep moving. So thermo means heat. Then the last one is dynamics, just a combination of two words. Thermo and dynamics means the heat is not what? Stagnant. So we need to learn about atmospheric thermodynamics because our atmosphere, as you can see from this earth, made up of mixtures, not only gases. A lot of things are also inclusive. Then, some of these mixtures, from there we discover that they can cause health challenges when we have pollutions, atmospheric pollutions, air pollutions, either from industrial, waste, or natural, or whatever. Okay? Sometimes we have haze in the, which is a particulate in the atmosphere. It's also a mixture. So how these mixtures behave under spatially varying temperature, that is the major agent. When we talk of climate change, all those change, atmospheric change, whatever change we are talking, the main agent is temperature. Temperature and pressure. So we need to study this as environmental scientists. One, we need to know what is going on in our environment. We need to let the government also know. Okay? which is very crucial to predicting the weather. We must be able to predict what is going on in our atmosphere in relation to the weather and, most importantly, the climate. Okay? Therefore, it is necessary for us to know all those laws, may not be all, but at least at this level, the necessary laws that govern the detail of these gases that is measured in our atmosphere. So the implications of energy that we are using mostly comes from our system, solar system. Principally, when we talk of solar system, it's from the sun. All the energy, talk of solar radiations, all type of radiations from the sun. We need to study to understand this, and this is the driver that is driving the relationship of the gases or the particulates that are made up of our atmosphere. So it is this interaction between the radiations, which I just said, and the gases that represent the atmosphere, which creates a temperature profile in agreement with the laws of thermodynamics. As we are discussing, that in agreement to the equation of states, structure of the temperature feed aspect, and then is very related to the social structure of pressure and density. When temperature feed, we talk of pressure, we are talking of the gases which I've mentioned, mixture of these gases that are made up of our atmosphere. It is this special variation of the pressure that drives the atmospheric winds. The wind you are moving from place, it is the special variation of the pressure in the atmosphere that drives these winds. And then more also, changes. When we talk of phase changes to liquid and liquid to vapor or gas or gaseous state. That is what I mean by phase. Play a lot of role in the climate system. Because of what? The cloud is made up of water, ice or snow, and then we talk of precipitation, which is rainfall, and so on and so forth. They are principally made up of water. That is why water has a bigger role to play. So therefore, thermodynamic processes govern these phase changes of substances. When we talk of atmosphere, what really is made up of our atmosphere? The principal component is nitrogen. We know about 80% made up of nitrogen, followed by oxygen, and we talk of water now. So this is a typical example of what we have. Blood form. As I said, a gas is composed of molecules that are free to move in any direction. No restriction. There are countless of collisions in between these molecules as the wind is driving, as the wind is moving, carrying it from place. There are collisions in between them, and when there is a collision, it results into what? Changing of their paths, their direction. They change directions, and then other actions that follow. When there is collision, energy is released, and sometimes the bigger molecules can break into smaller one, then collide again, like that. Sometimes smaller ones joining together to form bigger molecule. These are other actions that is really taking place in our atmosphere. Pressure in a gas, we know the definition of pressure is the force per unit area. So the force exerted by that material in a unit area. And what is the unit of pressure? Usually, commonly we use 1 atmosphere as unit of measurement. But the SI unit of pressure is Pascal, named after the man, Blaise Pascal. So 1 atmosphere equals to 101.325 kilopascal. And 1 Pascal equals to 1 Newton meter per second square. All this is just to refresh your memory. Then we have 1 by equals 1 by, which is in centimeter. Centimeter per second square equals to 10 raised to minus 1 Pascal. And the 1 bar equals 10 raised to power 6 of a bar, which is 100 Pascal. Then 1 millimeter mercury. Some devices are measured in mercury. Is equals to 0.133322 kilopascal, which is 1 torr. Just to flashback your mind to your undergraduate level when you study this. Now, what is an ideal gas? Which is equation 8. Describes the relationship among pressure, temperature, and density of earth materials. But in this case, our material, don't forget, is our atmospheric. So the relationship between the pressure, the temperature, and the density exerted by the component here, which is the gas we have, is described by an equation which we call an ideal gas law. And this ideal gas law states that gases are found to follow approximately the same equation known as equation of states. Atmospheric gases, whether considered as individual or as a mixture, obey an ideal gas law. Shown in the equation of gas law says that the pressure exerted equals the density rho, as constant R, and the temperature. So it is the density and the temperature that determines the pressure at a particular. This pressure is over area. We already know done in Pascal, and our density usually is mass per unit volume. So the mass is in kg for, and the volume is in meter per meter cubic. Therefore, the gas constant, the pressure, temperature 73.15, but mostly we ignore the 0.15, so we use 2.73 plus degrees Celsius. Degrees Celsius will be added to 273. So for a gas constant, the loss is very useful for the mixture of atmospheric gases or for the individual of these gases. The value of the gas constant for a certain gas depends on the molecular weight. So therefore, gas constant for a particular gas is equal to the universal gas constant R divided by the molecular weight of that gas. Universal constant 4 joule per degree per Kelvin. So if we know this, and then we know the molecular weight of a particular gas, we can always get the gas constant for that gas in the atmosphere. If you are given the gas constant and we know the universal gas constant, we can also determine the molecular weight of the gas in the atmosphere. The high atmospheric air is the molecular weight of that air, universal gas constant divided by the molecular, because it's assumed that nitrogen is about 80% of the component of our atmosphere. That is why we have 0.80 by the mass of nitrogen 2, and then oxygen is about 20%. So 0.2 multiplied by the molecular mass of oxygen 2. We know that nitrogen is multiplied, 2 of it will be 28. The same thing, oxygen, reminder. So 16 by 2 will be 32, 32 by 0.2, 28 by 0.8, all will give 28.8. That's our R star divided by the molecular weight of water vapor, which is 8314.8 divided by 18.016 is equal to 1. Just an example of what we have discussed. Degrees Celsius. In degrees with of density 6.67 by 10 in kilometer 100 Pascal. Using the Agde gas law, which we have discussed so far, the pressure for water vapor is equal to the density multiplied by the gas for water vapor and the temperature. Given the gas constant for water to be 461, then we can calculate the temperature. We first of all find in Kelvin, and then we can now convert to the, straight away we just put the parameters already supplied. We know the pressure for water vapor, density, and the gas constant for water vapor. So the density, and then, which is 0.5, and the gas constant for water vapor, which we have determined. So using a calculator is not difficult to find. If you find our answer in Celsius, in Kelvin, degrees Celsius, to get the final answer.